Hello, everyone. Good afternoon. I'm Pallavi, and I'm a postdoc researcher at Université, Montpellier. And I'm going to present TimeSenCLIP, which is a project under EU project like Granular. There is a collaboration between INRIA, CIHEM, CIRAD, and INRAE. So basically, TimeSenCLIP is a time series vision language model for remote sensing. Yeah. Just for a background. So basically, classical supervised models, we have satellite images, and you have classes, annual crop, residential areas, and those are like specific classes you have, and you train the model, it works really well. The moment you have some random text, kids playing in the park or cows grazing, those model doesn't work. You have to train every time the new model. So basically, we are for the supervised way of modeling is like label data dependency, which is like a classical issue. So we got lucky with vision language models, and which consist of basically the way models are trained are consisting of text and image. Those are learned jointly, and so these are like paired text and images, and the most similar similarity in the text and image. The highest the similarity, and it matches like a similarity score across the text and across the images. And that basically help enhancing the like usability in generic textual information, because since like CLIP-like model, which are trained on huge textual and image data set, so they are very much able to do like a text prompting. You just write a text and it can match with the images. Using this concept, we wanted to use for remote sensing, and there have been a lot of work already being done. But what are the issues? Why we have to adapt it to remote sensing? Why we have to train other models? If we have such big models which are trained on million of images, million of text pairs. First, CLIP type of models or generic computer vision vision language models doesn't have satellite representation very well. They are mostly based on like natural images. Second, data difference. We are from remote sensing community, so we know there is a lot of different type of multispectral, SAR, or different sensor type, different resolution, and also like less fine-grained context compared to generic natural images, which are high resolution often. And then also these vision language models, how they are trained are caption based. So you need text and image pairs. But we all know with remote sensing community, we know that data, labeled data is already a big issue. On top of that, having caption which actually explain satellite images can be really hard task. Therefore, in our previous work, SenCLIP, we did like a cross-view remote sensing VLM model, which what we did is we adapted CLIP embeddings, but we replaced text part to ground level imagery. So basically, a cross-view, so you have ground level images and you have geotagged satellite images, and you make ground level images as contextual labels to reduce the semantic gap between satellite images and ground level images. And in this work, we investigated like, can we have like ground level text prompting to actually effectively transfer to satellite imagery, like. Instead of just writing images that have annual crop, we can go like corn across the field or any layman terminology for the textual prompts. And we explored this in our paper, and we published this work at WACV. But what's the need of then TimeSenCLIP? We already had good performance with SenCLIP. However, most of the CV and existing remote sensing vision language models, they focus more on the spatial patches, like 224 to 512 pixels. Sometimes it can be possible that a lot of spatial information can turn into a rather noise information rather than useful signals. And also most of the vision language model existing remote sensing, they do not cover spectral and temporal aspect of the satellite images. So they fail to capture multispectral and information or seasonal effects of the rich information we already have in satellite images. So here what we did is we shift the focus from spatial context to spectral temporal context understanding. So here what we did is we focused mostly in Europe region, and we had for particular location a satellite image and geotech ground level shared location, and we have single pixel. So basically, it's not even a pixel, it's like a temporal and multispectral signal from that particular location. And then we have like ground level image for that, which has been for this particular data taken like in 4 direction. And then we trained the model where, because CLIP is already trained on like lot of natural images. So we hypothesized that it's already good at ground level images. And we trained time series multispectral along with doing the similar concept, just replacing text with the ground level images. And we tried to align both modality. So with this, what we got is a cross-view contrastive learning on single pixel Sentinel-2 time series, and which can also work on annual, quarterly, or monthly temporal sequences. This is the model architecture we use. So for temporal, to process temporal and spectral signal, we had, for temporal, we had extra temporal position encoding. And we kind of like, it's like 1 by 1 pixel. So basically it's a series of spectral and temporal information. And then we also kind of use some masking and dropout techniques to basically improve the, like, if there are missing signals, you can to regularize in a way. And we pass it through a basic transformer, and we train basically the temporal side, and we kept the clip frozen. And for the data set, we use Lucas EU dataset, which is basically, Lucas is like a huge European survey where they took like ground level images across Europe. And so basically 235,000 geotech locations. And for satellite images, we use SenForMap, which is actually Sentinel time series images collected using Lucas geotag locations. And they are like have 12 monthly composite and 10 spectral band. For evaluation, we didn't just wanted to stay like land use, land cover. We extended to habitat mapping, bioregion, crops, and different like scenicness, which is like kind of a regression task. So we did zero-shot classification on it, retrieval and regression. For temporal and we also evaluated on different temporal resolution. So single timestamp, seasonal dynamic with quarterly information, or monthly full annual phenology to test the sensitivity to temporal aggregation. And then we also evaluated on spatial patches, different number of patches. We trained like a 1 by 1, 5 by 5, for large context, 16 by 16. And then spectral resolution. So we also wanted to test like if RGB is enough or we actually need multispectral. I'm not gonna go to all the evaluation, just gonna focus on zero-shot classification. So for zero-shot classification, I don't know, but most of you, if you know. So basically what you do is you have, since we didn't train on captions. So for us, we just generated text prompts on all the classes from LLMs. And we used a CLIP text encoder because there is no text encoder in our modeling process. So we still use CLIP, which is already trained on a big data set. So we used CLIP text encoder and we match the similarity, and whichever text prompt get like a highest similarity score, you assign that particular text with the image, or in this case, temporal and spectral signal. So for our task, we evaluated across multiple geospatial tasks, and this is like, so we compared with CenCLIP, which has already like a CLIP-based backbone. So you process 64 by 64 image, and we also trained TimeSenCLIP, which basically we used CenCLIP embedding and we used our temporal encoder on top of it. So basically P64 is like 64 by 64 image, RGB, but single temporal. And then we have our TimeSenCLIP, which is multispectral and 12 temporal. And you can see like in all tasks, once you have multispectral and temporal information, the results improve drastically, especially for crops. Yeah. Overall, also we are compared against other state-of-art model, GRS CLIP, remote clips, and CLIP, and we see that spatial and also RGB or MS makes a lot of difference, but temporal information, once you have, even for single pixel, once you have multiple temporal information, results improve a lot. And I'm gonna skip. We also did per pixel predictions. So similarly, we did like zero-shot classification on each pixel of 64 by 64 patch. And if you can see, sometimes like labels are not correct, but then models still able to classify as at like a correct pixel, but there are definitely some noise because it's like pixel to pixel prediction. And we also did some text to image search. I don't have time, but I'm gonna. Also, what we found is like benefiting computationally, because since we are not processing huge patches, so 1 by 1 pixel is like memory efficient, smaller model you need, and it's very fast to process. So final takeaways are we were able to have stronger zero-shot performance. Temporal signal definitely gives a lot of benefit, apart from also having multispectral information, and we don't need captions. Basically, that's all. Thank you.
We have time for one question.
What was the size of the images that you used for the input? So you have one dimension that is spectral and another dimension that is time series. Then you have like 10 spectral bands.
Yeah, it's like 12 by 10 because we have 12 time steps and 10 spectral times, so it's like 12 by 10 basically.
And you used CLIP architecture that was treated on RGB, like.
No, sorry.
What did you use CLIP architecture? Standard RGB clip?
No, we didn't for this training. We didn't use CLIP architecture. It's like training from scratch. So we had like own position encoding and everything.
Thank you very much, Pallavi.